Guys, today we discussed here where we left. The question here is, in numerical analysis, we mainly consider here the distinct topics. But these topics are related with mathematics to approximate any approximation, any class, any branch of mathematics. So namely, we continue with, in previous we discussed root finding, and we discussed the solution, iterative solution of the linear systems. Now, today, we will talk about solution of nonlinear systems. But what is the thing here? So to go the nonlinear system solution, I want to actually give a brief introduction, give a brief reminder for you what we did in previous. In previous, we discussed the root finding with 3 topics, as well as them we discussed the coding in MATLAB. Okay, so the bisection method, Newton's method is also known as Newton-Raphson method, and then second method we discussed. We have discussed bisection method by considering here the main purpose here is to approximate the root, of course, but when you are doing this, you have a process because of the bisection. Bisection as a word, it's coming from divide into two section forms. So you have a magnitude and you will divide it into 2 parts. This division will be, in bisection method especially, you are getting here 2 divisions, 2 equal intervals. So to do this, we mainly focus on here an interval like AB and A and B values, and you will discuss here defining here A and B in the middle point. You are separating in the middle point, at the middle point, and you have here 2 different intervals. So the main idea behind the bisection method is intermediate value theorem. So we discussed here, is there any root in my interval, or which interval consisting the root? So we discussed this point by considering the intermediate value theorem, which is also considered as, here you can see the point f of a times f of c1 is negative or not. So if it is negative, you should choose here the interval that you are taken here into account will be a plus b divided by 2. If it is not, then you will continue with the previous, the next one. So of course you will check for, if you say no, then you will check here f of b times f of c1. Let us say c1 like the middle point in the previous approximation. So you will continue this process, as you can see, and we are repeating this process to get up to getting here the tolerance number will be whole, or the root will be obtained at the end. Then the second approximation will come from the Newton's method. The Newton's method is saying us iterational process. This is an iterational process, but the thing here is that, as you know, this is the best method as we know, according during these bisection, second and Newton's method. But the thing here is, it's coming from the problem can arise because of the derivative. The derivative can be maybe sometimes is undefined, or maybe it's so close to 0. So the problem occurs if it is 0, because then your solution will become, as you know, the undefined version. As we discussed in the class, actually we also discussed geometrically, and you know that the point of the initial guess is so important in this approximation. Okay, this is the initial guess, which is defined by us or maybe the user because of the computation case. So this x0 is so important as a choice of our method. So but to overcome this process, to overcome x0 choice problem, which is a challenging problem for us, we can also say that here, okay, maybe I can benefit from the bisection method. So bisection method can be helpful for the Newton's method also. Why? Because in bisection method you have also be sure about there exists a root. So in this interval, maybe you can split it into two parts as your C0, C1 case. Let me write here the C1. This is accepted as C1, for instance. Then your initial guess can be approximating as x0. This is considered as x0. This is a good expression, actually good approximation to discuss, to choose here x0. If otherwise is stated in the question, then we can also use here the bisection method that we are choosing here, that on which the interval we are sure there exists a root. Okay. The third method is called a secant method. The secant method is actually, guys, this is corresponding to the Newton process. They are so similar to each other. To overcome the problem which arises from the derivative, we have used here the derivative approximation. The derivative approximation is coming from where actually we have known that by the mean value theorem, as we discussed in calculus 1, mean value theorem says us, instead of the instantaneous velocity, which is corresponding to the derivative, we can also use the average velocity, as you can see. So the expression, as you can see here, the formalization. So if you are taken here your point xn plus 1 over xn minus xn case as the divisional part, this is xn plus 1 minus xn. This is corresponding to actually here, guys, f derivative at xn point. So we have used here instead of the derivative, we are using the approximation for the derivative. So, but it helps us. It helps us here, guys. We are considering here, it helps us to overcome the problem where f of 0, f prime is 0, or sometimes it is differentiable, sometimes it is indifferentiable forms. Then we can discuss here the secant method, take into account the secant method instead of the Newton's method. But all the time that we need to know about these, among these expressions, among these methods, we have known that here Newton's method is the best choice for root finding method. So we need to be emphasize this version, okay? So let's continue with here. Let's continue with our next slide. So in the second step, we have completed, guys, the root finding case in real numbers. As I said at the beginning, we discussed here all the time numerical approximation, numerical methods, not only for a subject, it is for all the approximation for the all branches in mathematics. So numerical methods is very important for applied scientists again. So you should know everything, every approximation and every analytical thinking on our course here. So what about the other thing? You know that in the nature, in the universe, we have not only a point. A point means that only you have a one axis, like x-axis. It is only a line, okay? So on the line, taking a point means that corresponding only a point. But what if we have, instead of a line, we have here Cartesian coordinates, or maybe, you know, in r cube or in r to the power n. What is then? How it changes? How can we find out the solution? So it is actually like the root finding case. So it can be also convertible in terms of the root finding case. But you need to know that now we are dealing with the systems of solution. As we discussed again our classes, face-to-face education, systems can be separated into two parts. First of all, nonlinear and linear version. So linear case is also discussed in the linear algebra case, for the linear algebra version, we also have here the directly solution. In the linear algebra, you have discussed by taking an augmented version and after eliminating it using Gauss elimination, and you can solve it by hand. Or instead of this, sometimes A inverse times B, if of course this is valid, this part is valid if, let me write it because it is important, of course it is valid if determinant of A is different from, is how can I write down, it is let me write, different from 0. Otherwise we cannot calculate A inverse. Then the matrix A is said to be singular. So guys, it is not our topic, it's not our subject. Because of this I'm skipping all these cases, but just I try to give here the cases. How can you find out the direct solution? Or instead of the inverse usage, you can use the decomposition. Okay, then the problem occurs here, guys. If we have 2 by 2 matrix, 3 by 3 matrix, okay, the inverse calculation is maybe hand calculatable for us. But what about if our dimension is getting bigger and bigger? So the problem arises then. Of course, we can use some computer programs to handle with it, but it also spends the CPU time for the computers. So for this reason, guys, sometimes it should be better if you can solve, if you can find your iterative solutions. So the iterative solution, in the numerical methods, we have Jacobi method and also Gauss-Seidel method. But as you know, we have skipped here the Jacobi method because it is very, actually this is the basis for Gauss-Seidel method, but because the Gauss-Seidel is giving a fast solution as well as it's the more accurate solution than the Jacobi method, so we have discussed Seidel-Gauss method. Okay, what about the Gauss-Seidel method? It says us to apply Jacobi, does not matter, Jacobi or Seidel, you should use here, you need to be sure about the given system is the diagonal dominant. The diagonal dominant here, if I'm not saying here, otherwise it's stated, guys, we just accept the diagonal dominism like the strict diagonal dominant. But you need to know that the strict diagonal dominant will give you here your diagonal entries will be the bigger one in the absolute values, of course, the bigger one, the biggest one of the summation of these row elements. Okay, so here is the model of the diagonal dominism. Here you can see that this is the model for our expression, so it is so important for your understanding. Okay, after putting here, after being sure, we are sure about the diagonal dominism. If we say yes, all the system is the diagonal dominant, then we can discuss here the iterational process. The Gauss-Seidel method uses the idea, the idea is here, I'm saying now, the use of the point that you have already obtained. So in previous, for instance, in the first step, you can see what I mean here. In the first step, I don't know what about here x2, x3, x4. In previous, we don't have any knowledge about it. Then to discuss here x1 k plus 1, the superscript says us here, guys, the our iteration numbers. Okay, this is the iterational process for us. Then after finding the x1 k plus 1, so because it has, we have already have an existence here, we have a knowledge information about x1 k plus 1, so use this expression in the next step. So it is the process, use what you obtained. Okay, so it is now the Gauss-Seidel method. according to this review, I have discussed here all these things what we did. You have also done, guys, the coding cases for these subjects, for these topics. So it is enough to give a review session. Let's continue with here the Newton-Raphson method for systems. What about nonlinear system? Now we will continue with it.